Welcome back. So since the papers have just been released, I've decided I'm going to make videos covering all of them. That's going to be IGCSE, AS and A2. Now, as always with these videos, I will recommend also checking the mark scheme because of course I won't be able to cover everything. There'll be things in the mark scheme which I don't say. Yeah, and of course if the video is too slow then you can watch at 1.5 or 2 times the speed. Okay, so question 1, the size of a file can be measured using different data storage units. We want to tick one box to show the smallest data storage unit. Right, okay, so I guess really we just want to convert them to a kind of a common unit. So if we think byte, well of course what byte is going to be 8 bits. And I guess actually here we don't really have to do this, but just to demonstrate how you'd actually, work this out, yeah, kind of more formally. Now if we think gibi, now when you see gibi, of course, right, you want to think, well that's in terms of power, 1024. Right, now if you think kibi, well kibi is 1024 to the 1. Right, maybe that's going to be 1024 to the 2, right, therefore gibi, well that's going to be, 1024, well, cubed, right, equivalently we can also write that as 2 to the power of 30, and the reason for that is because if we think 1024, well that's equal to 2 to the power of 10, yeah, therefore just kind of indice laws, 1024 cubed is therefore equal to, well, 2 to the power of 30, yeah, that's just, again, like mathematical indice laws. Right, and again, because this is bytes, well then of course we have to multiply that by 8 if we want to get that into bits. Right, if we think kibibyte, well kibibyte we said what that's going to be just 1024. Again, of course, right, because it's bytes, well then we multiply that by 8. And then if we think nibble, now this one, I mean, if you know it then, well this should immediately stand out as being the answer. Right, nibble, that's only going to be 4 bits. So of course, yeah, that's going to be our answer there. Now, of course, in the real exam, you can just sort of instantly see that quickly. However, I'm just showing the working because let's say you have another question asking, how many bits are in a gibibyte. Well, hopefully now that you've seen the working, right, yeah, now you should actually know how to calculate this. Okay, and I guess that's kind of what we have to do here then. Right, we want to state how many tebibytes, right, TIB are equal to 2 pebibytes. Okay, so if we think, well, we said gibi was 2 to the power of 30, therefore tebi, right, that's going to be 2 to the power of 40. Pebi, right, I guess that's going to be the next one, right, that's 2 to the power of 50. Right, however, of course, we can also write this in terms of 1024. So what we can actually say, and let's actually start here from bytes. Now, if we say, yeah, okay, right, so 1024 bytes is equal to 1 KIB, right, 1 kibibyte. Okay, yeah, sorry, okay, right, let's go 1024 bytes is equal to 1 kibibyte. Right, then we can go to the next one, so 1024 kibibytes, well, that's then equal to 1 mebibyte. Alright, and again, the reason for that is just what kind of these power rules we set up here. So what we can say, that pattern is basically going to carry on, right, so 1024 mebibytes is equal to 1 gibibyte, 1024 gibibytes is equal to 1 tebibyte. Right, therefore 1024 tebibytes is equal to 1 pebibyte. However, of course, because we have 2 of these, well then we just have to multiply that by 2. Alright, so here that's going to be our answer, 2048. Now of course, like, because these are both in bytes, well then we don't have to do any conversion there. Yeah, and I guess they did give us some space for working as well. Right, then C, the size of a file needs to be reduced. Give the name of the process that's used to reduce the size of a file. Okay, so hopefully people know that's going to be compression. And of course compression, well we've got 2 kind of umbrella terms, right, lossy and lossless. Now when we say lossy, basically this means that some of the data is permanently lost. So we're going to have the original file, yeah, let's kind of say, alright, so I'm going to sort of draw it like this. Right, we're then going to compress it, and when we then get the kind of output, well here we've actually lost some of the original data. Yeah, if you can sort of, see the height difference. Alright, so that's going to be lossy, where basically, yeah, when we compress, we would have actually lost some of the data. Right, so that means that when we actually decompress, when we go back the other way, well then we're not going to be able to reconstruct the original again. Right, so some examples of lossy, if we think about images, sound, then you really just want to think about the formula. So for example, the file size for for images, that's going to be what the resolution, right, the resolution being the number of pixels in the image, right, multiplied by, well, the bit depth or color depth, basically how many bits are used per pixel. So let's just call that B. Now what you can of course think, right, because we're multiplying these together, well if we reduce the resolution, right, then of course the file size is going to go down, Right, likewise, if we reduce the bit depth or color depth, yeah, again, the file size is also going to go down. All right, and we can also think the same with sound. So sound, I guess what the formula was going to be the duration, right? Then it's multiplied by the number of channels, or in fact, actually, let's kind of do this the other way. All right, so first, what's going to be the number of samples? Yeah, okay, right. Yeah, okay, right. So the number of samples are basically the sampling frequency, right? How many samples per second? Right, then I guess, yeah, again, you can call it the sampling resolution, right, or you can call it the bit depth. So that's going to be the number of bits for each sample. Right, then you want to think, multiplied by the duration. Now, generally, you don't really want to change the duration of sound because, either you're going to be, cutting off some of the start or the end. Yeah, or if you're, speeding it up, then, of course, you're kind of permanently changing the actual kind of property of the audio. Right, and I guess, yeah, also then you're going to multiply by the channels. Now, if you've got mono audio, right, you only have one channel. For example, if you have stereo audio, stereo audio, then you're going to have a left channel, right, so what's coming out of your, left speaker, left headphone, right, and you're also going to have a right channel. So effectively here we've got 2 times as much data, of course, because we've got, left data, right, left channel, right, and of course, data for the, audio coming out of the right channel, right, the right headphone. Okay, so of course if we reduce that down just to a single channel or mono, right, then of course that's going to halve the file size. Alright, and here I guess we're just looking at 2 channels, okay, but of course these channels, they could be 8, yeah, it could be 16, if you've got some, professional stage, for example. Yeah, so I guess that's quite a lot about compression, alright, but generally make sure you're confident with all of those. You also want to think, let's say run length compression, yeah, I guess that's really the main one. Sorry, not run length compression, or run length encoding. Yeah, I guess RLE. Right, that's going to be the main one they also mention for images. Right, and run length encoding, that's going to be lossless because we can actually get the original back. Right, anyway, so yeah, that was kind of quite a ramble. Yeah, that's why I do say, watch it sort of 2 times if you want, or yeah, 2 times the speed. Right, then the next one, one reason the size of a file name may need reducing is so that it has a shorter transmission time. Give one other reason why the size of a file may need reducing. Okay, so I guess we can just say save storage space. Yeah, save storage space, maybe on hardware. Yeah, that should be fine. Right, so can we think of any others? Right, so shorter transmission time. I guess this is kind of related. I mean, what we can say is going to use less bandwidth, because let's say you've got like a mobile phone and maybe you don't have unlimited bandwidth. Alright, so if you only have, I don't know, 50 gigabyte monthly limit, you don't want to be sending, a 20 gigabyte sort of full HD movie, or downloading a 20 gigabyte full HD movie, because I mean that's going to use up 20 of your 50 gigabytes, just in one go. So yeah, I guess we can say, right, it's going to use less bandwidth. Of course, it's faster, right, shorter transmission time. Right, save storage space. You could probably also say save money because I guess yeah, okay, right. So there's kind of 2 reasons. Obviously, one, you're using less bandwidth. I guess yeah, that's really just related to this, right? You're saving money because you're not having to buy as much storage. Alright, and I guess another one they often mention is if there's some sort of file size limit. A lot of email clients, they have a 25 megabyte limit. I guess even a lot of social media apps, you're not going to be able to send like a 5 gigabyte video on most social media websites, or apps. Alright, so yeah, okay, so maybe then you want to compress it, just so you can actually upload it or send it. Right, then number 2, a clothes store has a ticket system to allow customers to speak to a personal shopper. The ticket, the ticket displays a ticket number in hexadecimal. For example, 11B, 11B. The ticket system has an output device that creates a paper ticket identifier and an appropriate output device to produce the paper ticket. Right, okay, so I guess here they just want a physical copy, right, therefore we can just say printer. Yeah, printer. Now you could be more specific and say like an inkjet printer, but yeah, I think just saying printer here is going to be fine. Yeah, alright, okay, and actually, yeah, alright, so you could say inkjet or laser. Now, I think for IG you don't really have to remember the differences now. Basically, yeah, right, okay, so just to sort of do it quickly. Right, if we think an inkjet, an inkjet is basically dropping, I guess, kind of ink bubbles. Now, if we think about an ink bubble, I'm going to sort of try and draw the shape. Alright, so imagine this is a bubble that's dropping. Now when this hits the paper, the problem with this is basically, because it's a bubble, well then it's going to kind of spread out. So this is okay for images, but if for example we want a kind of crisp text, then actually inkjets are not that good. Because we get this kind of blur effect as we kind of drop the bubble. Alright, so that's where we would really want a laser printer. Now the advantage of an inkjet is basically because we're actually using liquid colours, you can kind of get like higher quality colours. Whereas if we think a laser printer, well, a laser printer is basically using powder. I guess technically they call it toner. Alright, but basically it's just like a chemical powder. It's like a just powder. It's like a kind of grain, different grains. Alright, and I guess with toner you can't really get high quality or kind of vibrant colours. Whereas with inkjet you can. But I guess in this situation, I mean, if it's just a black and white ticket, alright, I think a black and white ticket you'd say probably a laser printer. If you want some high quality colour, ticket, right, then you'd probably want to go with the inkjet. Although to be honest, that's probably more of an AS kind of question. I think they don't really ask about the differences now in IG. Right, anyway, the next one, so each ticket number is stored as a binary number in the ticket machine. Ticket numbers 14B and 97A. Convert the two ticket numbers from hexadecimal to binary. Okay, so sometimes I see people sort of converting to base 10, right, and then obviously it was obviously denary, and then obviously from denary converting back to binary. And I guess that kind of makes sense because I guess as humans, we're of course just used to base 10. However, actually that's more complex for this situation. Now, if we want to go from hexadecimal to binary, right, or vice versa, okay, binary to hexadecimal, then what you have to think, basically there's a relationship because we say, so I guess 2 to the power of 4 is equal to 16. So effectively what this means is, 4 bits, right, 4 bits is equal to 1, hexadecimal digit. Alright, so what we have to think is basically we're just going to treat these hexadecimal digits as kind of individual. And then we're just going to convert them to binary individually. So the first one here, right, just this 1. Well, then we're going to convert this 1 into 4 bits, right? So that's going to be 3 zeros, then a 1. Right, then the next one, right, then we want 4 bits for this next one. So that's going to be obviously, there's no 8s, right, there is a 4, but obviously no 0, no 2s, no 1s. Right, then if we think B, A is 10, therefore B is 11, right, and 11 in binary, that's going to be 8, right, it's not going to be a 4, but then it's going to be 2 and a 1. Alright, and these are actually quite easy to check if we want because, so the way we can check is basically just do the reverse process. So of course here, here this is just a 1, right, in binary. The next one, here we see that's just a 4 in binary. And the next one, we've got an 8, right, we've got a 2, we've got a 1. So that's going to be, 11, right, and of course 11, that's just B. Alright, so here we've got 14B. Alright, and again, of course, the reason I show you how to check is that in the exam, of course, it is kind of recommended to check your answers, if you have time. Right, so, alright, what you can do, I mean, you can pause the video, have a go at this yourself, right, try and use the same logic. Alright, so let's have a go then. Right, so this one, it's going to be an 8 and a 1. Right, then the 7, that's going to be, 4, 4, 2, 1. Right, then A, that's going to be 10, so that's just going to be an 8 and a 2. Right, and hopefully that makes sense how that all works. Right, then we want to give 2 reasons why the ticket number is displayed as hexadecimal instead of binary. Okay, now if we think binary, I mean, this is quite complex for humans to understand. So let's, and because we're talking about, really the benefits of hexadecimal, let's say, right, hexadecimal, let's say what is easier? Easier for humans to remember. Humans, or let's say, to understand and remember. And sorry about the handwriting, but it's kind of difficult to write on this tablet. I think I kind of screwed up by buying a cheap tablet. Right, anyway, then the next one, I guess we can say it's going to use up less kind of physical space. Alright, and if you actually say it uses less space, usually they won't give you the mark for that, because that's kind of ambiguous. I mean, do you mean less storage space, as in data, right, using less bits? Alright, because in reality, actually in a computer, everything is just stored as binary. Of course, right here they're talking about, physically printing it. but sometimes they'll say, why do we represent data as hexadecimal sort of on a computer? Or why do we display it, as hexadecimal, right, to the user? Now, if you say it uses less space, right, they actually won't give you the mark, because in reality, well, 1 is just using the same space, because as we've seen, one hexadecimal digit is just 4 bits, right, so basically they're equivalent. Because of course here, right, right, so here we've got 3 times 4, because obviously 3 characters each using 4 bits, but then that's 12, and then obviously here we've just got 12 bits. Alright, so what you actually want to say, you want to say less physical space, or less space on paper. Right, so I'm probably not going to write the whole thing, right, let's say hexadecimal, alright, let's say uses less space, less space on paper. Okay, and like maybe you'd want to expand that. I think probably that's okay. Alright, and of course just in the exam, just write it out fully, but I just sort of did that just to save a bit of time. Right, the next one, the ticket numbers could also be represented as denary. Convert the 2 ticket numbers from hexadecimal to denary. Right, okay, so this one's actually a bit more complex. What we want to think, we just want to write out the positional values. So the first one, well, this is 16 to the power of 0. 16 to the power of 0, well, that's just 1. Alright, the next one, that's 16 to the power of 1. Alright, so that's going to be 16. The next one, right, 16 to the power of 2, so that's going to be 256. So what we're saying, basically what we've got, well, 0 times 256, right, then we're going to plus that with, 2 times 16, right, and then we're going to plus that. Now, let's sort of do the C. Okay, so again, we think A is 10, right, therefore C is going to be 12, and 12 times 1, and I guess we don't really need to write this multiplied by 1, because of course, well, that's just going to be 12. Alright, so if you add that all together, then I guess, 2 times 16, 32, right, plus 12, that should be 44, if my maths is not wrong there. Right, then basically we can just do the same here, so I'm probably not going to write it out. In the exam, I guess maybe you'd want to. Right, so what you say, so right here is going to be 256, and then B, right, that's going to be 11. So 256 plus 11, right, that should be, 267. So then we just want to go the other way by converting the 2 denary numbers into hexadecimal. Now the way we can do this again, we just want to write out the positional values. So if we think the first one is just going to be 1, right, then we're going to have 16, and then we're going to have 256. Now if we see here, well, 109, right, that's smaller than 256, therefore we actually don't need this. Right, we only need to go up to the 16th position. So we want to think, well, how many times can we divide 109 by 16? And I guess if we think 5, so so 5 16ths will be 80, right, therefore 6 16ths will be 96, and I guess 7 is going to be too many. So here then there's going to be 6 16ths, right, and then then we're going to have 13 left over, right, because of course 6 16ths is 96, right, therefore 109, right, minus 96 is going to be equal to 13. So 13, and there's going to be 13 ones, and 13 is going to be D, because A is 10, right, B 11, C 12, so yes, right, that's going to be D. Right, this one, so I guess a bit more difficult. Right, so of course, this is bigger than 256. However, it's not going to be 256, because 256 is going to be 12. Right, so here we're going to have 1 256. Right, then we want to think, how can we actually subtract that? So let's go for 415, and to be honest, you can probably do this in your head if you want. So 5 minus 6, right, so here we have to borrow, so let's just go 0. So right, 15 minus 6, that's going to be 9. Right here, 0 minus 5, well again, that's too small, we have to borrow. So here we have 10 minus 5, that's going to be 5, and then 3 minus 2, right, that should be 159, if I've not made any mistakes there. Right, so actually we can think, if it was 160, right, because we're on the 16th position, then 160 would be 10, which is A, right, therefore I guess here this means we're going to have 9. Right, so I guess 9 is going to be, 144, right, so that should mean there's 15 remaining, and 15, right, that's just going to be F. Okay, so hopefully that makes sense what I've done. So of course, 1, right, that's going to be 256. And okay, actually the thing is we can actually test this quite easily, or we can, check our answers. So if we go, right, 256, right, and then 9, so what you said, 9 is going to be 144. Yeah, I think that's fine. Right, then f, that's going to be 15. Right, then if we add all those together, well, hopefully we should get 415. So let's just do this quickly. Right, so that's going to be well, this is going to be 15. Right, carry the 1. Right, 6 plus 4 and then plus 1. Right, that's going to be 11. So carry the 1, and then yeah, so well, 1 plus 2 plus 1. Right, so that's 415, which gets us back to our original. Right, then number 3, an image is converted to binary to be represented by a computer. Complete the table with the missing terms and definition about representing an image. Right, okay, so the first one, this is the smallest component of an image. Yeah, that should be pixel. Yeah, I mean, I guess that's the usual definition they use. Sometimes, okay, yeah, alright, so sometimes they also say, well, what does pixel stand for? Right, so what you can say, actually, that's going to be picture element. So, of course, well, the PI here, right, yeah, okay, and then element, alright, and then, yeah, the EL here. I mean, honestly, like, where the X comes from, I guess they just kind of add that. Alright, but you can also say that's kind of the definition. Right, so a pixel, well, yeah, it's the smallest component of an image, yeah, representing each picture element, or yeah, kind of each color. Okay, right, then the next one, and yeah, sorry for the cough. Right, so the resolution, that's going to be the number of pixels in the image. You can also say what the number of pixels wide by the number of pixels high. Let's probably say that, yeah, the number, right, number of pixels, let's say wide. Yeah, I guess, or you can say what the number of pixels are kind of in the columns. Right, the number of pixels wide, yeah, let's say by the number right, of pixels high. Right, let's go, yeah, i.e. Right, i.e. Let's say the total. Okay, yeah, total number, right, of pixels, right, in the image. Yeah, alright, and I guess really this is really only going to be for bitmap. If we're talking about vector, then of course, well, vectors are not really going to use pixels. Yeah, I guess they would be kind of rendered, right, kind of well, using pixels because, you know, the screen is pixels. But yeah, their actual internal, you know, mathematical representation. Well, of course, right, that's going to be obviously, well, lines, coordinates, yeah, things like, well, you know, radius. Yeah, obviously if it's a circle. Yeah, I guess things like, well, you know, different colours, right, different properties basically. Right, then the next one, this is the number of bits used to create each colour in an image. Right, so I think this is what we said, basically this is what the number of bits for each pixel. So again, this has two names, either we can call it what the bit depth. Yeah, alright, yeah, okay, right, so here you can call it the bit depth, right, or you can call it the colour depth. Yeah, both of those should be accepted. Right, then the last one, this is additional data that's stored with an image that can provide information such as the time and date that the image was taken. Right, so if we think, and really this is not just for images, this is, I guess, a lot of formats, or yeah, a lot of file formats. Right, so as well as the actual data, well, first you're going to have the header. Alright, and I guess here, well, we can call this data. I guess you can really call it payload. Yeah, I mean, payload is maybe more for kind of packets, right, when you're transmitting something. If you're just, you know, storing it on the sort of a hard drive SSD, right, then I guess, yeah, probably you can just call that data, to be honest. Alright, and yeah, some file formats are also going to have a trailer. I think, okay, yeah, I think, for example, a PDF, right, a PDF is going to have a trailer. Yeah, yeah, okay, right, of course, as well as a header as well. Yeah, now here it's just talking about some of the metadata, for example, the time, I guess, yeah, things like the author, right, the camera model, the sort of geolocation. Right, however, there's also more things that are fundamental. In fact, let's just write this. Yeah, let's say, well, file header. Yeah, or I guess we can probably say image header if we want to be more specific. Right, now actually in an image header there's also going to be more things that are fundamental to actually displaying the image or, you know, representing the image. Right, so some of the things that are going to be stored, well, one is going to be the resolution. Right, we're also going to store, well, the bit depth, the color depth, and we're also going to store things like the sort of file type. Right, so yeah, whether it's you know, JPEG compression, yeah, whether it's, you know, PNG, right, whether it's a GIF, etc. Right, now, I mean, it should be kind of fairly obvious why we need the file type, because of course, well, it's different algorithms. yeah, different kind of, you know, storage, yeah, I guess kind of storage structure. Alright, however, why we need the resolution and the bit depth, color depth. Now, let's just say we've got the payload here. Now, of course, this is just going to be basically a long, a long stream of kind of binary, right, bits. So let's just say we have, I don't know, some random bits like this. Now, the thing is, the kind of image software. Now, if we don't know the resolution, then we actually don't know kind of how wide and obviously how high to make the image. Likewise, if we say, well, the bit depth, color depth. Now, if we haven't been told that, now how do we know, for example, whether maybe say these 4 bits, you know, represent 1 pixel, right? Or perhaps maybe it's, you know, these 8 bits that represent 1 pixel. So yeah, that's why we actually need the bit depth, or, you know, well, bit depth, color depth, yeah, in the file header, or yeah, in the image header. Because what you can then do is, let's say we're told that the bit depth is 4, well, then basically the kind of image parser, right, it can then basically split this on groups of 4 pixels, right? Therefore, we would know, well, this is obviously, you know, pixel 1, right, color 1, right? This is obviously pixel 2, right? Yeah, the next 4, that's obviously pixel 3. And let's say, for example, we're told, yeah, let's say this is some, you know, super small, like 2x2 image. Now, what we can think here, let's just sort of do that for, right, what we can think here is, because we're told it's 2x2, well, then what we know is, of course, well, this one here, right, this is going to be the top pixel, the sort of top left, right, this pixel 2 here, right, that's going to be what, 1100, right, now because we got to 3, well, because basically 3 is sort of, you know, kind of on the next row, yeah, and the way you'd actually do that is probably by using modulus to calculate, you know, what row you're on. Alright, then we would know that, of course, well, yeah, this is then going to be the pixel here, and then obviously, well, this last one, yeah, sort of 4, right, that's going to be the pixel here. Alright, and again, that's kind of going off topic, but I think if you actually kind of understand this on like a deeper level, well, then when it asks, you know, what's stored in the image header, right, then you should be able to think, well, what would the actual image software need to actually correctly represent, or yeah, correctly display the image, right? And hopefully now that you understand this, well, you should sort of instantly know, well, of course, we're going to need the resolution, because we need to know when to start a new row, right? And of course, we also need, well, the bit depth, color depth, because we need to know kind of, you know, when to break up, yes, or when to break up this bit pattern, right, into the individual pixels. Yeah, alright, so again, hopefully that makes sense, yeah, why I've tried to explain that. Okay, so I think my laptop just shut down from overheating when I was recording this. Yeah, unfortunately I can't use the fan because, well, that's kind of too loud when recording these videos. Alright, but I think this was the question we got to. So number 4, a restaurant has an electronic ordering system. The system allows customers to select the food they want to order. The data for the order is transmitted across the network to a computer in the restaurant kitchen. The data is sent using serial full-duplex data transmission. And give 2 reasons why serial full-duplex is a suitable data transmission method for the data. Okay, right, so here then, because it's talking about 2 reasons and they've kind of given us, I guess, yeah, 2 kind of factors to talk about. Right, so first then let's talk about, well, yeah, why serial is kind of advantageous. Alright, so I think there's a few things we can say about serial. One is going to be reliable. Alright, the reason it's reliable basically is because we're not going to get skewing. Now, when I say skewing, if we're talking about parallel transmission, right, so let's say we've got a parallel transmission and we've got, what, 4 wires here. Now, the problem is that some of the data can be out of sync. So let's imagine we're trying to send, I don't know, you know, okay, yeah, something like this, right, 1001. Now, maybe this 1 has already arrived, but, you know, this 0 is kind of lagging behind a little bit, right, and actually, yeah, okay, right, so maybe this 0 has, you know, arrived even earlier, right, and then, I don't know, yeah, this 1 is even slower. Alright, so yeah, the problem we get, basically, yeah, okay, right, this is called skewing, where either the wires are actually kind of operating at slightly different speeds, I don't know, maybe some, you know, hardware problem, yeah, or I guess, I don't know, it's just not synchronized properly. Right, so then let's say we then want to send, you know, another, well, yeah, okay, right, so I guess here is what can be a nibble, where it's just 4 bits. Now, we might actually have it where, let's say we're sending another nibble here, I don't know, you know, 0000. Well, what we can actually have is we might have something like this, where now we actually have a situation where, let's say this 0 here is going to arrive at approximately the same time as this 1. So the receiver might actually think that, you know, obviously, well, this 0 and this 1 are the same nibble. right? And if they think that, well, then of course the data is going to be corrupted. Right, okay, yeah. So they're going to get the sort of wrong number at the end, or the wrong data at the end. All right, so hopefully that makes sense. Whereas if we're talking serial, well, because serial is literally just one wire, right? Then of course, well, first we send a 1, then we send a 0, then we send a 0. Obviously, then we send another 1 here. Kind of looking at this, right? So yeah, hopefully that makes sense, right? Because they're sent one after the other, right? Then they're going to arrive in order. Let's say that let's say reliable, and in order. Let's say in order, receiving of bits guaranteed. Receiving of bits is guaranteed. Guaranteed or sort of extremely likely. Due due to there only being a single wire. This is kind of just repeating myself, I guess. Due to let's say due to bits being sent sequentially sequentially along a single wire. I think that's sort of not really worded very well, but yeah, hopefully people understand what I'm trying to say there. Probably in the exam you might want to think about how you're going to word it a little bit better. Alright, so maybe here you'd also want to say no skewing. Alright, I'm just going to sort of draw an arrow there. Again, probably if this was in the exam, I would have had to think about how I'm going to word that a little bit better. But yeah, I guess I don't want to take too long on the video. So then I guess full duplex, and in fact, in fact, let's also talk the other advantages of serial. So serial you can also transmit over a long distance, and again that's because sort of skewing is not going to become an issue. Now if we think here, so let's say we've got parallel over, say 1 meter, well maybe skewing is not really an issue, but if for example we want to send over 100 meters, well then you can imagine things are going to get more and more out of sync, right, the sort of longer we send that. Hopefully that just makes sense, intuitively why that's going to be. Alright, because let's say for example here, maybe this one is going, 1% faster. Well, of course, 1% faster over 1 meter is going to be like a 1 centimeter, it's arrived, 1 centimeter, kind of in advance effectively. Whereas of course, if we're talking, over, 1 kilometer, well then if this one is traveling 1% faster than, this one, right, then of course that's actually going to be a big physical distance, or a big physical gap between them. Alright, and you'd probably want to relate this back to the restaurant example. So you could say, so parallel is good for short distance. Usually, say like 2 to 3 meters. Right, that's why a lot of cables are short. You often don't get some, 100-meter cable, and if you do, probably that's going to be serial. If it's a long cable. Alright, and I guess you say what, because the restaurant is big, or probably the restaurant might be big, then I guess like a 2 to 3 meter distance is not really suitable for a restaurant, right? Hence why you're going to need serial. Alright, and you can also talk about the speed. Now if we're only they're selecting food, so it's probably just selecting some food ID. If you think about a database, right, you're going to select this ID for the main course, right, this ID for the dessert, this ID for the starter. Right, again, probably you're going to be adding some toppings, right? Maybe just some simple comment, about how you want the food to be cooked, for example. So in reality, you're not actually going to be sending, that many bits, that many bytes of data. So yeah, you can say here, well, serial is going to be sufficient, for the small amount of data that we're sending. Now, if, for example, you're talking about, live streaming some HD video, well, then of course you're going to want parallel, because you're going to need that higher bandwidth. Right, so let's look at the second one, full duplex. So the advantage of full duplex, and again we want to relate this back to the restaurant. We can say, well, two-way communication will be required, because, well, from the customer to the restaurant, of course, well, they have to place the order, but also from the restaurant to the customer, well, maybe they have to notify them if their order has been a success or if their order has failed. And if their order has failed, right, then they probably want to give a reason why. For example, let's say, some of the ingredients are out of stock, or something like that. So I think we can write that. Let's say full duplex, Right, full duplex right is used right because because well, two-way communication right, two-way communication is required. Right, and yeah, let's give examples, right, e.g. Customer right placing order, yeah, and let's say restaurant notifying customer, right, notifying customer, yeah, I know, right, of order status, right, let's say e.g. what a success, I don't know, yeah, unavailable, or like, yeah, sort of dish unavailable, right, unavailable, yeah, I guess, etc. Right, okay, then the next one. So give one improvement that would be made to the data transmission if parallel transmission is used instead of serial transmission. So I think we mentioned that for the video streaming. What would you say, faster? Yeah, I guess well, faster or higher bandwidth. Yeah, that should be okay. Let's say faster slash higher bandwidth transmission. Yeah, okay, we're higher bandwidth. Yeah, higher bandwidth transmission. Right, and I guess we can explain that. Right, let's say i.e. Yeah, i.e. well, I know, you know, more bits can be sent in the same time. Right, more bits can be sent right in the same, yeah, I guess in the same time or in the same given time. Right then, B, so a checksum is used to check the data for errors after transmission. Describe the process of the checksum error detection method. Right, okay, and here we want to kind of, yeah, I guess highlight this right after transmission. Okay, because, yeah, these questions about, I guess, well, sort of verification, verification, validation, they do want you to specifically talk about, yeah, whether it's, well, before transmission, so I guess data entry, yeah, or whether it's, you know, after transmission. Alright, so I guess if we think about data entry, what some of the ones they usually say are what double entry check and visual check. Whereas if we're talking about yeah, sort of verification after transmission, well, I guess, yeah, one, that's going to be a checksum. Alright, also what a parity check, echo check, yeah, and also ARC, right, automatic repeat request. Yeah, so make sure you're familiar with all of those. Of course, well, parity, I mean, that's just counting how many how many even ones, or, you know, so yeah, how many even bits there are. Yeah, obviously echo check, well, just sending the data twice. Yeah, okay, sorry, right, so A sends to B, or yeah, you know, the sender sends to the receiver, right, the receiver sends back to the sender. And if the sender gets the original data back, well, then it can assume that, I guess, the receiver has, you know, sort of correctly received the original data. Yeah, and alright, okay, so ARC, I mean, that's going to be a bit more complex. What positive, positive or negative acknowledgements. Basically just sending the data. What there's going to be a timeout, and if, for example, they successfully receive the data, well, then it will send a positive acknowledgement saying that it's, you know, sort of successfully received it. Right, if the sender doesn't receive that positive acknowledgement, well, then it will wait, let's say a given time, right, a timeout, let's say, I don't know, 3 seconds. Right, if it's not received the positive acknowledgement after 3 seconds, well, then it will send again. Right, and basically, if it doesn't receive the positive acknowledgement again, well, then it will, for example, send again. Right, it's then going to have a number of times to try, let's say, for example, I don't know, 5 times. And if it tries 5 times without receiving a positive acknowledgement, then it can just stop, because then it will assume, I don't know, there's some network problem, or yeah, the, you know, device is offline, for example. Yeah, alright, so just make sure you're familiar with all of those. Right, but then if we talk about checksum, so what we can say, and I guess it's 5 marks, so try to think, well, 5 points, 5 keywords. And yeah, to be honest, right, in the exam, I mean, a lot of people, it helps, you know, maybe they can just write a simple plan, you know, before sort of writing these, yeah, for these sort of, you know, big questions. Alright, but I think I'm just going to probably start writing it. So what we can say, I guess, first, what we can say that an algorithm is agreed, you know, by the sender and receiver. Yeah, okay, let's say a hashing algorithm, or like a checksum algorithm. Right, let's say a checksum right, algorithm right, is agreed on right, by, well, sender and receiver. Yeah, and I guess, you know, that might be based on a protocol. So let's say, I don't know, some protocol, let's say like FTP, for example. Now, maybe FTP is always using For example, I don't know, like SHA-256, it's just the default algorithm. Yeah, I'm not really sure, but okay, yeah. So some protocols might have just one kind of checksum algorithm or hashing algorithm. Yeah, others they might have to actually negotiate amongst themselves, sort of seeing which one they both have available. Right, anyway, so yeah, checksum algorithm is agreed on by both the sender and receiver. Okay, right, let's say the sender then I guess what performs, let's say performs, or yeah, I guess executes, performs the algorithm, on the data or on the payload. Yeah, I guess here they just said data, so let's just call it data. Let's say data, what they are about to send. Yeah, let's say to generate a checksum. To generate, yeah, I guess the checksum. Alright, and we can basically say, I don't know, like a number or string or a sequence of bytes. Yeah, let's say, sequence of bytes. Sequence of bytes. Then I guess once they've generated this, then they will send both the data, the payload, and the checksum. Let's say that the sender will send, let's say both the, I guess payload, payload and checksum, to the receiver. Okay, receiver. Okay, and I guess who will perform, or yeah, maybe we should say the receiver again. Alright, let's just start a new sentence. Let's say the receiver, yeah, or we could say, I don't know, once received. Yeah, this is assuming it's been a successful transmission. Yeah, alright, okay, let's kind of say that. Okay, let's say once received. Yeah, I think I can't spell received. Once received, yeah, the receiver, receiver will perform the same algorithm, or yeah, the same checksum algorithm. Same checksum algorithm. Let's say, yeah, on the data they have received. And then what we want to do, so if the checksum we generate is equal to the checksum that the sender sent, then we can assume there's been no transmission error. So let's say that if the checksum, yeah, let's say the receiver, receiver, yeah, generates, is equal to the to the checksum that the sender sent. Yeah, then we can assume the transmission has been successful. Yeah, then we can assume the transmission has been successful. Alright, and I think here, because we talked about what happens if it's a success, let's also talk about failure. So I think for failure we can, I don't know, yeah, let's say else the data is requested to be resent. Yeah, I think that seems like a sort of suitable thing that we might do. Let's say else, yeah, let's say that, the data, yeah, let's say data and, recalculated checksum, are requested to be resent. Alright, and the reason I've said, the checksum should be recalculated is because maybe actually the sender sort of made a mistake when calculating the checksum. Yeah, I don't know, maybe there was some sort of weird, I don't know, sort of CPU error. Yeah, and that can be caused, I don't know, some static in the CPU, this sort of, modified one of the register values. Yeah, some kind of, weird, unexpected error like that. Alright, yeah, okay, and yeah, the reason I say that it's not a bug is because, if it's a bug, now then you'd have, the same error again. So it's not going to be a software bug, it's going to be, I don't know, some weird, hardware bug, or yeah, some weird, I don't know, sort of like interference, right, coming in from the outside. Right, anyway, so then number 2, we want to identify one other error detection method that could be used to check for errors in the data. Right, now this one is a bit ambiguous, but I think here, because they've said after transmission, right, we can probably assume they're also talking about after transmission here. And I think here we've mentioned a few of them, right? We said, well, echo check. Yeah, so I guess, well, echo check. We could say parity check, or we could say ARC. Yeah, so automatic repeat request. Right, then C, a customer can also order food from home using the internet. The data for their order is broken down into packets and transmitted across the internet to the computer in the restaurant kitchen. Right, tick one box to show which item would not be included in the packet's header. Right, okay, so in a header, well, yeah, there is going to be, well, the destination address. Of course, that's going to be IP address. IP address. Right, well, the source, right, the originator's address, yeah, that's going to be there. Right, the packet number, yeah, that's going to be there. The reason you need the packet number, basically 2 reasons. Right, one, you have to make sure that you've actually received all of the packets. So let's say you receive packet 1 and packet 3, right? But of course, well, then you're going to think, well, where's packet 2, right? Then you can ask for that to be resent. Right, the packet number, and I guess this is really more common, basically it's used for reordering. So if, for example, you receive, I don't know, packet 3, right, then packet 1, then packet 2, well, then of course you can think, well, yeah, okay, right, so of course now you just need to reorder them, yeah, in the correct order. Right, okay, so yeah, right, in the packet's header, well, we're not going to have the payload, alright, because just like we said with the file header, basically they're going to be 2 separate things, right? So first we're going to have the header, well, then we're going to have the payload, right, or the data. Yeah, so even though it's going to be part of the same packet, of course it's actually, you know, sort of different parts in the packet. And to be honest, right, if people want to see this in more detail, there is a good program called Wireshark. Yeah, so people can sort of download that. That's going to be free to download, and basically you can see all of the packets both, well, coming in and sort of outgoing, right? So your incoming and outgoing, and I think by default it's going to be just on your computer. Although I think you can actually get it working where it can actually kind of listen to all of the traffic, yeah, sort of going in and out of the router, so even other people on the network. Yeah, of course, right, okay, yeah, so of course, well, you want to be careful. Like in theory, you know, if say it's other people and they sort of haven't given you your permission, then I guess that would actually be illegal if you're, you know, listening into their data. Although of course, well, it should be encrypted as well, so you won't really be able to understand it. Yeah, although I guess okay, yeah, so things like this won't be encrypted, right? Things in the header won't be encrypted. It's only actually going to be the payload that's actually encrypted. Right, so the packets of data may need to be reordered when they arrive at the computer in the restaurant kitchen. Explain why the packets of data may need to be reordered. Alright, so yeah, we kind of briefly hinted at this. I guess, yeah, right, so there's kind of 2 reasons. One is because if we think about packet switching, right, so just sort of using routers, yeah, sending this packet onto the next router, right, obviously from that router onto the next router. Basically packets can travel different different routes along the network. So let's say maybe packet A might go to this router, right, then to this router, then to, I don't know, let's say the sort of final destination here. Whereas let's say another packet, well, maybe first it goes to the same router, but maybe here it detects that, I don't know, okay, yeah, let's say this router might be congested, yeah, or this router might be offline, right? Then, for example, it might send it to this router instead, right? Then this router, then this router. Alright, and yeah, what might happen is, let's say because this is congested, well, maybe that's slow. So actually we say packet 1 has actually arrived after packet 2, yeah, because of the, you know, this slow router here. So let's try and say that, let's say packets, yeah, packets can be routed, I don't know, yeah, via different routers or along different routes. Let's say, I don't know, yeah, via, and yeah, I guess, well, different routes, right, that should be fine. Via different routes, yeah, let's say along the network. Yeah, let's say what, hence, I don't know, yeah, hence will travel at different speeds and might arrive out of order. Yeah, let's say may, okay, yeah, alright, let's sort of word that a bit better. Right, hence may take different times to arrive. Right, different times, yeah, to arrive. Right, and yeah, I guess, yeah, and hence arrive out of order. right, let's say, I don't know, yeah, resulting in corrupted data. Resulting in corrupted data. Yeah, I guess we can say what this, yeah, alright, okay. And again, like, maybe this is not worded the best. Right, let's, okay, I'm just going to delete that. Right, okay, so they're going to arrive out of order. Right, let's say, yeah, if not reordered. Right, if not reordered correctly. Yeah, reordered correctly. What, yeah, the data, okay, right, the data, yeah, will be corrupted. Yeah, okay, so hopefully that makes sense. Right, and I did say there's actually two reasons. So yeah, one, well, obviously packets can go different routes. I mean, you can also say that if, let's say, okay, yeah, let's say this one here is just completely unavailable. So what we've then got is, well, here we've had, obviously, packet 2 has arrived, right? But then, of course, well, because packet 1 has to be resent, well, yeah, then packet 1 is going to arrive later. So really, it's kind of just the same thing. So I guess here we said, well, they may take different time, right? But we are assuming they both arrive successfully. If we actually have some packets that don't arrive at all, well, then, of course, it's going to have to be resent. Right, and then if it's resent, well, then it's definitely going to arrive out of order. Yeah, alright, so hopefully that kind of makes sense. Then number 5, data is processed by the central processing unit CPU in a computer as a von Neumann architecture. We want to complete the table with the missing terms and definitions about processing data. Right, the first one, current instruction register. So I guess we can say this will hold the instruction that's currently being decoded and executed. Yeah, let's say that. Right, holds the, well, I guess instruction or current instruction. Yeah, alright, so I think saying, well, again, current instruction, we're kind of just repeating this. But yeah, I'm not really sure how else to word that. Alright, holds the current instruction. Yeah, I don't know, being decoded. Right, being decoded and executed. Yeah, alright, and I guess you could mention what after it's been fetched from memory. Yeah, because of course, well, first it's going to be loaded into MDR. And then obviously from the MDR, well, then it's copied into the CIR. Yeah, but I think I'm not going to write that. Now the next one says this is a processing unit within the CPU that can fetch, decode and execute instructions. Now I'll be honest, when I first looked at this I was actually a bit confused. Yeah, I did actually have to check the mark scheme sort of what to see what they said. Now immediately I was thinking the control unit. Now the control unit, I mean that makes sense for decode because, well, the control unit does decode. However, I mean it doesn't really fetch and it also doesn't really execute. Now if we think about fetch, we can say, well, the control unit does contain the system clock, and of course when the system clock ticks, well, that's going to be the start of a new fetch, decode, execute cycle. So in particular what we would say is basically a sort of read signal would be sent on the address bus to read a specific address. Right, okay, yeah, so I guess actually, well, it's going to read the address in the program counter, right, obviously, well, from, well, RAM, cache, right, wherever that's stored. Alright, and that's going to be read into the NDR. Alright, yeah, so again, right, the control unit is kind of responsible for, okay, no, sorry, right, so the control unit contains the system clock, and of course, well, the system clock, when that ticks, right, that's going to be the start of a new fetch, decode, execute cycle. Right, however, it's not actually the control unit that's doing the fetching. Of course, it's the actual, well, I guess, yeah, it's kind of just, you know, data being sent back on the wires, or yeah, sent back on the data bus. Likewise for execute. Now, while the control unit kind of, I guess, does have some kind of behavior, you know, sort of to do with execution, it's not actually executing itself. So let's say if we have, I don't know, for example, an add instruction. Now, hopefully we know that add is going to be performed by the ALU, right, the arithmetic and logic unit. If, for example, we have, let's say LDD, right, so LDD, well, that's a load instruction. In particular, well, D, right, that's going to be direct. You actually don't have to know for IG. Basically, that just means, well, load data from memory. There's also other types, right, LDM, that's basically just loading a number. But yeah, okay, right here, load direct, that means, well, load from memory. So if, for example, we do an LDD, well, that's then going to be executed by one of the memory components, right? That could be RAM, that could be cache. Yeah, I guess it could even be secondary storage, possibly. Yeah, although probably not, because we generally don't want to sort of well, load directly from secondary storage, because, well, that's going to be like extremely slow. Alright, so how this kind of relates back to control unit. is because basically the control unit is going to be responsible for sending the signals. So if we've decoded the instruction and we realise that it's an add instruction, well then the control unit will send a signal to the ALU, right, telling it to add what the current contents of the accumulator, with whatever is kind of sort of stored in this add instruction. So this could be just a number, right? So then it's going to add the number with the contents of the accumulator. This could also be an address, right? Now if it's an address, well, first of course we would have loaded that data into the MDR. Right, then the ALU, well then it's going to take the data in the MDR, right, of course add it to the accumulator. Alright, so hopefully that makes sense what the control unit's role is, because sometimes they say, what's the purpose of the control unit? And you say, well, one is going to contain the system clock, right, used to start each fetch, decode, execute cycle, obviously synchronize the instructions, right? I guess the main one, where it's going to be used for decoding the instructions, and what that means is, because basically everything's going to be binary. So let's say we have, some instruction like this. Now basically we're going to have what the instruction set, and the each kind of instruction in the instruction set is going to have its own opcode, right, its own binary code. So let's say for example instruction 4 zeros, right, maybe this is LDD, right, just load. Let's say this one, kind of instruction 3. Well, maybe instruction 3 is add. So here we say, well, this is going to be an add instruction, right? We've decoded that because so let's say we've got some simple 8-bit CPU where we say the first 4 bits represent the opcode, right, the actual instruction. The next 4 bits, well, this represents the operand, the data, right, the address. And let's say in particular this is just add the number, right? So basically I kind of add in the just kind of add in whatever this number is. Now here of course we see, well, this is going to be 9. Okay, so hopefully that makes sense what decode is. Decode is going to be taking this whole instruction. So what this whole instruction was 0011, obviously 1001, right, obviously those 8 bits, right, then obviously breaking it down into the opcode, the actual instruction, right, and obviously the operand, the actual data. Right, that's what decoding is. Right, and I guess that's kind of similar to what I said about images, where you're obviously going to have this long stream, long stream of bits, and they basically have to be kind of split into the individual pixels. That's kind of what we're doing when we're decoding, right? We're splitting this into the opcode and the operand. Right, and then when we talk about execute, so the control unit's responsibility for the execution part, basically it's going to be for sending the signal to the correct component to execute that particular instruction. So again, if it's an add, well, it's going to send a signal to the ALU. Obviously, if it's let's say like a load, right, well then it's going to send a signal to the memory components. And I guess technically actually it's going to send that on the control bus, right, either a read signal or write signal, and it's also going to send the address, right, to read or write from. And I suppose if we're writing, we're also sending data on the data bus, right? And again, this is kind of going off topic, but I guess just to give some specific examples can help solidify the point. So let's say we actually want to write some data. Let's just think, right, so here this is the data bus, right, then I guess what we've got the address bus, and also the control bus. So effectively what we're saying is if we want to write data, well, we're going to send a write signal, and maybe we say, 0 means read, and let's say the 1 means write. Right, on the address bus, well, this is the address we're writing to, and let's just say, for example, let's just go for example 4, right, so just 4 in binary, and let's say the data, maybe that's just going to be 5. Right, so hopefully this makes sense what we're doing. That basically, so we're sending 5 on the data bus. We're saying, well, obviously, this data is going to address 4, and here we're sending on the control bus, we're sending, the signal 1, right, which corresponds to write. And we're basically going to need all 3 of these buses, right, in order to do a write. If we think about a read, well, read we actually don't need to send any data because of course, we're sort of getting data incoming, right? So here, let's say we're and let's say this is going to be 0 because let's say 0 means read, for example. So here this means read from address 4, right? That's going to be sent to the different memory components. The cache is going to look, and if the cache contains address 4, well, then it's going to send the data back, right, on the data bus. If the cache doesn't contain address 4, well, then obviously RAM is going to be next, right? If RAM contains address 4, well, then of course RAM is going to send the data back, on the address bus. All right, so again, that's kind of quite a off-topic kind of spiel. But yeah, hopefully that just explains, or hopefully that helps kind of with people's understanding of how this works. Yeah, because I do see people saying, what's specifically sent on the data bus, or what's sent on the address bus control bus. Alright, but anyway, yeah, so even going after all that, okay, the answer here is actually not the control bus, because as I said, the control bus is for decoding, but it's not really for fetching, it's not really for executing, it's kind of, I guess kind of indirectly, right, but it's not sort of directly doing that. Right, so here they actually just say core. Right, because I guess each core is just like basically a mini processor. It's going to contain all of the registers. Right, so yeah, PC, MAR, MDR, CIR. Right, I guess things like the status register, index register. Yeah, it's going to contain it's going to contain its own cache, right, its own control unit. Yeah, basically just a mini processor. And of course, if we have multiple cores, then we can execute multiple instructions independently, right, and simultaneously. Right, so next one, this is a list of all the commands that can be processed by the CPU. Right, that's going to be the instruction set. And in fact, yeah, actually let me just show you this one, because I do have this here. So yeah, if we just open this one, right, asmcode.pro. Okay, so that's finally loaded. Now, if people do want to have a sort of play around with this, yeah, you can see the instruction set here, right, expand, you can see the different examples. You can also, for example, go down. So for example here, let's say LDM, right, we're just basically loading a number, right, we say, that's going to have to say this machine code, basically just 1. Alright, and you might think, why does this not start from 0? Because obviously here we say what instruction, or machine code 1 is this, basically loading a number. Obviously here LDD, that's loading from memory, right, obviously instruction 2, right, instruction 3, instruction 4, instruction 5, yeah, etc. If we go down, we see, here the end, right, just terminating the program, right, that's instruction 0. Right, but hopefully this makes sense what the instruction set is. Basically just the list of all of the instructions that particular processor, right, or processor family supports. Alright, and again, this website, asmcode.pro, this can also be good, for example, if you step cycle here, right, you can actually see how the different registers, right, PC, MAR, MDR, right, etc., kind of how they're changing. Yeah, okay, so that can be quite good if you want an actual practical example of this. Yeah, and you can sort of, even create a trace table. Although I guess a trace table is not really for, IG, right, that's going to be an AS thing. Yeah, tracing assembly. Alright, so if we sort of go back here, right, the next one then, cache. So I think cache, there's a few keywords they want. One, they want fast, it's going to be temporary. And I guess memory. So let's say fast. Right. Let's say fast temporary. Temporary access memory. And we can say inside the cores or shared between the cores. Or I guess you can say inside the processor. Let's say fast. Short term or temporary. Temporary. Temporary access memory. Let's say stored in let's say in or between, or I guess shared between the cores, shared between CPU cores. Right, then let's say what it stores. So things that are going to be stored in the cache, one is going to be currently used, commonly used. Right, so commonly used instructions and data. Commonly used instructions and data. So let's say you have a loop and you're looping over, I don't know, 1,000,000 times. Well, you don't want to have to, sort of load in that data 1,000,000 times, or load in those instructions, from RAM 1,000,000 times. Right, therefore you can store it in the cache, which is going to be faster and closer to the CPU. Well, I guess, even, inside the cores. Right, therefore when you have to load it 1,000,000 times, well, of course that's going to be much faster, right, since it's a, shorter distance it's having to travel. And I guess the actual kind of components themselves are actually faster as well. So stores commonly used instructions and data. And I guess it can also, and also sort of let's say stores pre-fetched instructions. Let's say commonly used. Let's say here, and pre-fetched. Alright, now again, this is kind of going beyond the scope of IG really, but when we say prefetching, now what this means is, let's say we have some instructions, and let's say currently the program counter is on, I don't know, 500. right? Now, probably what we think, well, of course, it's going to go right 501, 502, 503, right, etc. Right? Eventually, of course, it's probably going to get to, I don't know, say 600. So rather than it getting to, let's say, 599, right, and us not having, instruction 600 in the cache, right, what we can actually do is we can think, well, because we're on 500, in the not too distant future, eventually we're probably going to get to 600. So what we can then do is, let's say we can we can load all of the instructions from, let's say, memory address 600 to 700, right? We can load these 100 instructions into the cache, right? Then of course we're going to execute, well, obviously, 501, 502, 503, right? Then of course when we get to 599, well, rather than then having a long wait going to RAM, right, we've actually already loaded, these next 100 instructions into the cache already. Right, so maybe that makes sense. If it doesn't make sense, well, you can just search, cache prefetching if you're curious. If you want a sort of more kind of real-world example, I think the easiest example to think of is, let's say you're calling a taxi. Now, you could, go out, right, so let's say you're in a hotel, you're in your house. Now, you could obviously, walk out of your hotel, right, wait on the road, obviously, call a taxi. The problem with that, well, maybe you're going to have to wait 5 minutes, right, maybe 20 minutes, depending on where you are. Obviously, that's not really very good. So that's kind of what we were doing if we weren't using prefetching, right? We're just saying, well, currently we're on 500, right? Obviously, we're then going to execute 500, right? When we finish executing 500, well, then go and load 501, right? So that's actually not good because we've actually finished instruction 500 before we've even started to load 501. Right, alternatively, going back to the taxi example, what you could think is well, in 20 minutes, I'm going to need a taxi. Right, therefore you can of course call the taxi company, 20 minutes in advance, right, when you're still in your hotel. Right, then of course by the time you're ready, by the time you've walked outside, well, the taxi should be, kind of waiting outside for you. Right, so that's basically what prefetching is. You're basically kind of loading the instructions before you need them, so that when you do need them, well, they're already in cache. Right, they're already, fast to access. So when you need them. Right, then the last one, the accumulator. So we can say what it stores the results of the currently executed instruction, or the currently executed arithmetic or logic instruction. I guess, well, the most recently executed. Right, let's say stores the result, right, of the, well, most recently, most recently executed, I guess, well, arithmetic. Right, arithmetic or logic instruction. I think that kind of makes sense. Alright, and the reason I say arithmetic or logic is because let's say if we're doing, let's say like a load, well, we're of course going to load the data into the NDR. So in that case, we're actually not loading it into the accumulator. Alright, so something like an LDD, well, an LDD is not going to use the accumulator. The accumulator is only used for arithmetic, obviously mathematical, right, and logical, and, or, XOR, right, not, etc. Even things like the logical shift, right, so for example LSL, right, logical shift left, just moving the bits left, moving the bits right. Right, this one I think we said, right, identify the component in the CPU that's responsible for decoding an instruction. So, right, that's going to be, well, CU, right, the control unit. And of course it's better to write the whole name, and we don't just write CU. Right, then C, we want to explain how the clock speed can affect the performance of the CPU. So what we can say that basically on each clock tick, and I think we've said this, right, on each clock tick, basically that's going to be the start of a fetch, decode, execute cycle. So if we have basically a kind of, well, more clock ticks per second, well, then that means, more fetch, decode, execute cycles going to start per second, right, hence more instructions executed per second. Alright, and I guess, maybe this is not necessarily performance, but you could mention that if we increase the clock speed too high, then of course, well, because of overheating, right, the CPU can actually get damaged, and I guess in that case you're actually decreasing the performance because, well, of course you've damaged the CPU. Right, so let's try and say that, let's say, maybe on each, right, let's say on each clock pulse, right, a new FTE, right, a new, let's just write that, right, fetch, decode, right, execute cycle is started, Right, let's say hence, hence if we increase the clock speed, increase the clock speed, then more, then more FTE cycles, and I'm going to put in brackets basically instruction executions, because that's kind of what we're saying, right? We're saying, well, more instructions are executed per second. Executions, will occur or will start. Will occur right in a given time. Let's say e.g. each second. Okay, I mean, hopefully that should be enough. Right, let's maybe mention about the kind of overheating, also called overclocking. Right, let's say, however, if increased too much, let's say overclocking, overclocking can occur, let's say leading to overheating, overheating, maybe, and potentially permanent damage of the CPU. Potentially, permanent, permanent damage, to the CPU. CPU, I guess, hence degrading performance. Let's say hence degrading performance, in the long term. That should be okay. Right, then number 6, so data can be encrypted using asymmetric encryption. Complete the paragraph by asymmetric encryption. Use the terms from the list. Some of the terms in the list will not be used, and you may use the term more than once. Okay, so with these questions, I always think it's a good idea just to read through all the words first. I mean, obviously, algorithm, that's going to be a sequence of instructions used to kind of achieve a task, perform a task. Binary, of course, just base 2 number system. Right, ciphertext, so that's basically going to be the result. Let's say the result of the encryption. This is like the output, right? The encrypted text, basically. Obviously, compression, taking some data, making it smaller. It could be lossy, lossless. I mean, error, I think everyone knows that. Obviously, hardware, physical components. Obviously, hexadecimal, base 16 number system. I think meaningless, we don't really need to discuss. So plaintext, this is going to be the original unencrypted text. So of course, you're going to take the plaintext, you're then going to use the encryption algorithm, along with the encryption key. That's then going to convert the plaintext into the ciphertext. So private key, of course, that's going to be a key that you don't share with anyone, you keep it to yourself, store it on your device. Public, that's going to be a key that is shared with everyone. And in asymmetric encryption, I guess, maybe I'll do a diagram in a minute. The public key is used for encrypting. Readable, I guess, just is it understandable? Obviously, transmission sending, unreadable. Okay, so let's just try and sort of get a diagram of how this works. So let's say we've got A and B, and let's say that A is sending to B. Okay, now actually what we can say, basically both of them are going to have a public key and private key, if we want two-way communication. So let's say here, they got, so A has a public, A has a private. B, B also has a public, B has a private. Now, if we say that A is sending to B, now what they're going to do, let's just go PT, so PT is the plaintext. So what you're going to do, you're going to take the plaintext, you're then going to plus it, and I say plus, I mean it's obviously not like an actual addition, but it's just obviously using the plaintext, plus this plus something else, in order to get the ciphertext. Alright, so what we're going to need, we're going to need B's public key. So let's just write that. Let's say B pub. So again we take the plaintext plus B's public key. Plus let's say the encryption algorithm. This thing. Then basically that's going to spit out the ciphertext. CT. So again, just to kind of reiterate. So A, so obviously A has the plaintext, A has the original message they're going to send. They then take the encryption algorithm, of course that's going to be agreed on by both A and B. It could be, for example, RSA. RSA is a common asymmetric encryption algorithm. I think it just stands for, Rivest or Rivest, Shah and Edelman. Basically the 3 surnames of the people that invented it. Right, and then well, B public key. Yeah, and of course again, right, so this is public. And the reason that this is public is because, well, basically anyone has to be able to encrypt, right? Because not only might we have A and B, but let's say we also might have C. Now C might also want to send something to B, and again, basically they're going to do the same thing, right? So C is going to use B's public key in order to encrypt. Yeah, that's why B's public key has to be publicly available to anyone, because yeah, anyone might want to send a message to them, right? And yeah, so this might not literally be a person. In reality, this is more likely to be, for example, a web server. So let's say A, well, this might be you, well, yeah, your, internet, yeah, your, web browser. Right, B, well, this is going to be some web server that you're trying to visit. And of course, yeah, that communication has to be encrypted. Right, then when we talk about decryption, so basically, because these pairs match, now sometimes I see people thinking, well, they're going to use, I don't know, say B's public key and A's private key. But actually, these are completely unrelated. So you're never going to be like mixing and matching keys like that, because yeah, basically they have no like mathematical, similarity between them. Yeah, there's no relationship between them. All right. So when you're encrypting, you're always going to be using the same pair of keys. Likewise, if you're creating a digital signature, again, you're always going to be using the same pair of keys. Right, so what's going to happen then is, well, because we use the public key to encrypt it, well then when B receives the ciphertext, right, B is then going to use the same encryption algorithm, well, in order, right, and I guess we can call it a decryption algorithm, but it's basically the same thing, right, the same algorithm. But of course, right, then they're going to use the private key, right, yeah, they're going to use their private key. All right, so hopefully that makes sense. Now, if, for example, yeah, just to solidify this point, now let's say, for example, B wants to send something to C, and again, remember, okay, right, C is going to have a public key, C is going to have a private key, right? So you can pause the video if you want to have a think about how this is going to work, right? Again, B is sending to C. So what's going to happen? Well, B is going to have their own plaintext, right? Then they're going to take what's C's public key. So let's say, yeah, C public key, right? Then, of course, by the encryption algorithm, right? When they obviously run this, right? Then they're going to get the ciphertext. They're going to send this ciphertext to C, right? C is then going to use its private key in order to decrypt that. Yeah, so hopefully that makes sense. Now, right, okay, yeah, and that's going to be for asymmetric. Now, if we're talking about symmetric encryption, well, symmetric encryption, that's going to be a little simpler. So here, so here A and B, well, they're both going to have one key. Alright, so this is going to be the same key for both of them. Now, while that's simpler, because I guess you don't need to generate, multiple keys, right, the disadvantage is that basically there needs to be some way of A sending the key to B, or let's say B sending the key to A. Alright, but the thing is, really this key is supposed to be private. We don't want a third party, for example C, right, getting access to this key, because if C does get access to the key, well then of course they can decrypt anything that A and B sends. They could also encrypt, so they could also, for example, pretend to be A, right, they could encrypt a message and send it to B, and because it's encrypted, well, B will then be able to successfully decrypt it, right? Therefore, B is naturally going to assume that's coming from A. If they get some message that they can't decrypt, well, then they would potentially be suspicious. They might think, well, who has this come from? They've probably used a different key. But because here they've obviously used the same key because I guess they've stolen it, right? Then they can also send messages to B, and B could actually believe that this is coming from person A. Alright, so yeah, hopefully that makes sense. Yeah, alright, and with that knowledge, hopefully we should be able to answer these. Right, so data is encrypted using an encryption key. Right, this is a type of something. Right, now here, this is kind of weird. They say algorithm. Yeah, although I would actually disagree with this. Because actually, so the key itself is not actually an algorithm. The key itself is just data. Alright, so this could just be, some, sort of password that you type in. Right, so this could just be, ABC123. Right, that could be your encryption key. In reality, this is probably going to be something sort of like randomly generated. However, I guess you can sort of manually specify as well. Alright, so I would actually say this is not an algorithm. Really, this is just data. However, for some reason, I guess in a lot of these past paper questions, right, they always call the key an algorithm. So yeah, that's something you just have to remember. That's some weird Cambridge quirk, to be honest. Right, so anyway, this is the type of algorithm that scrambles the something and turns it into something. Right, so this is what we said. Right, so this is going to be the plaintext. Of course, yeah, the plaintext is the original message. Right, and then ciphertext, well, that's going to be the encrypted message. Right, this makes the data, I guess, yeah, meaningless. Or I guess, yeah, okay, right, probably unreadable is probably a better one here. Yeah, I think unreadable kind of makes more sense. Right, a something key is used to encrypt the data, right? So again, because we're talking about asymmetric encryption, because, well, that's what we've said here, right, asymmetric. Right, then we said, right, to encrypt, right, that's going to be a public key. Alright, and I guess in particular, it's actually going to be the receiver's public key. Right, this key cannot be used to decrypt the data, right? Instead, a something key is used to decrypt the data, right? That's going to be private key. Right, any device is able to request the, well, that's going to be public key, because as we saw, both A and C, right, A and C are both able to get B's public key. Right, well, however, yeah, but only your device knows the private key. Yeah, okay, because I guess you don't want to give that to other people. Because let's say, for example, if, okay, yeah, so let's say if C managed to steal B's private key, well then B, yeah, okay, right, then C would be able to decrypt, right, anything that A is sending, right, because of course, well, they've got B's private key. And again, the reason that works is because basically when these are generated, they're basically kind of generated using the same sort of like input numbers. So because of this, yeah, they kind of have this relationship. Right, that's why you can't, you know, mix and match, say A's public key with B's private key, right? Because yeah, they're completely unrelated. Right, data can be encrypted, yeah, also be encrypted using symmetric encryption. Give one reason why a person would use asymmetric encryption instead of symmetric encryption. Right, so this is what we said. Basically, asymmetric encryption is more secure because we don't have the issue of having to transfer the key. Now, as we said, right, if we've got A and B, now the problem is, let's say if A has some data, well, let's say plaintext. Now the thing is, right, okay, A is going to encrypt it using its key, right? Okay, this is for symmetric encryption. Right, however, the thing is, right, A also has to somehow, right, give this key to B, okay, because, well, B is then going to need this same key in order to decrypt. So again, let's say, I don't know, let's say ABC123, right? So yes, somehow, right, A is going to need to send this to B. Alright, however, of course, well, the problem is, well, what if someone intercepts that? So yeah, that's kind of the problem of symmetric. Right, so yeah, okay, that's why asymmetric is better because it's more secure. Let's say that, yeah, let's say, right, it's more secure. Right, it's more secure, right, than symmetric. Right, than symmetric encryption. Yeah, I guess what, because one key is always kept private. Right, because one key, yeah, is always, right, always kept private. Right, and I guess what we can say, I know, yeah, never, right, never has to be sent. Yeah, I know, yeah, never has to be sent, right, over the network, for example. Right, yeah, e.g., yeah, e.g. never. Yeah, never sent, right, over a network. Yeah, I think that kind of makes sense. Right then, 7. So a student's computer has primary storage. One example of primary storage is random access memory, or RAM. Right, identify one other example of primary storage. Right, so I guess the obvious one, well, that's going to be ROM. Yeah, and I guess we could say, you know, obviously, well, read-only memory. Yeah, if you want to write that in full. Right, and let's, yeah, okay, and I guess we can also say cache. I mean, you could say registers, although to be honest, I would say cache and registers, I mean, they usually don't mention those in the mark schemes as much. So yeah, I think for primary storage, you know, stick to the obvious ones, right? That's going to be, well, RAM and ROM, those two. Okay, now the definition of primary storage, basically there's just one definition, or I guess, yeah, one sort of main definition, and that's that this can be accessed directly by the CPU. Now, if we have secondary storage in contrast, now secondary storage, okay, yeah, alright, so I guess in theory there are ways to directly access, but, you know, generally it can't be directly accessed. It first has to be stored in an intermediate location. So let's just draw a diagram here. Right, let's say, okay, yeah, this is the CPU. Right, let's say, I don't know, let's say, what, PS, so primary storage. So for example, primary storage, obviously RAM, right, ROM, or yeah, obviously, registers, cache, etc. Right, and let's say, well, secondary storage, that can be, well, obviously hard drive, right, or let's say, yeah, SSD, right, USB, etc. Now, if, for example, we have something in RAM, well, something in RAM can just be directly loaded into the CPU. However, let's say we have something in secondary storage in the hard drive or SSD, well, we generally can't sort of directly go from there, to the CPU. Alright, so let's just erase that. So instead, what we first have to do is we have to go, well, from the hard drive into RAM, right? Then, of course, from the RAM, well, to the CPU. So of course that's going to be slower. Okay, so yeah, that's kind of related here. So right, explain why RAM is an example of primary storage and not secondary storage. Let's say, well, since RAM, what can be directly accessed by the CPU, directly accessed, accessed by the CPU. CPU. Let's say, what, when reading and writing data. And honestly, I mean, right, okay, I was a bit confused about what to write here for 3 marks. Because really, I mean, okay, yeah, that's only the sort of solid definition. I mean, that's only the thing that's 100% true, right? So primary can be directly accessed. I did actually check the mark scheme for this, and this is something that people sometimes say, sometimes not, because it's not 100% true, right? Now, sometimes people say that primary storage is going to be volatile, and secondary storage is non-volatile. Now, that's generally true. However, there is one exception, right? Now, if we think volatile means when you turn off the power, then the data is lost. So if we think about RAM, well, anything in RAM, or let's say, I don't know, this current document, the game you're playing, right? When you turn it off, of course, well, your progress is lost, right? Likewise, cache registers, right? When you turn off the power, that data is lost. All right. However, ROM, well, ROM is going to be an exception. Right, so that's why primary storage. I mean, primary storage is generally primary storage is generally volatile. I mean, at least 3 out of 4 are. Of course, yeah, obviously, well, 1 is not. Whereas if we say secondary storage, well, all of these are non-volatile. So what this means is when we turn off the power, the data actually stays. So again, going back, let's say here, we've got obviously hard drive, SSD, right, USB, optical storage, so DVD, Blu-ray, CD. Things like magnetic tape, I think USB I said, right, SD card. Alright, so all of these, they're going to be, well, non-volatile, right, permanent storage. So let's say that, with the exception of ROM. ROM, let's say, what primary, primary storage, primary storage, right, such as RAM. Such as RAM, registers, registers and cache. Cache. Terrible writing. Right, so cache was CACHE. Are volatile. And then maybe we should just explain what that means, because, well, we've got extra space here, right? It's also 3 marks. Are volatile. Let's say meaning. Meaning once the power is turned off, once power is lost, once the power is turned off, or lost, right, / turned off, then data is permanently lost. Permanently lost. Alright, I think that makes sense. Right, so then C, the student is editing a large video file for a project, and during the process the RAM becomes full. This makes the computer crash. Describe how virtual memory could be used in this process to stop the computer from crashing. Right, okay, so yeah, do I have space to draw a diagram? Maybe not too much. Alright, let's sort of go down here. Right, okay, so let's say this is our RAM, and I'm just going to draw virtual memory as a circle. I mean, that's usually what they do. Now, usually RAM, well, either it's going to be split up into pages, and pages will be fixed size. I think on Windows, pages are going to be 4 kibibytes usually. So if you've got, let's say like 16 gibibytes of RAM, well then of course you're going to have thousands, possibly like millions of pages. Right, so I'm just going to sort of draw here, lots of different pages. Obviously, well, like, page 0, page 1, page 2, page 3. Obviously, page, sort of 1 million. Right, now if you're talking about segmentation, right, these segments can actually be variable sizes. So I guess one segment could be, I don't know, say let's say 5 mebibytes. Maybe another segment could be, I don't know, 500 for example. Yeah, although paging is generally more common, where you're going to have fixed size. Right, okay, so what we'd have now, let's say if here all the pages are full. So if we have, I don't know, yeah, okay, right, let's say we have like 1 million pages and all of these 1 million pages are full. But let's say we have some other program which we're trying to load, or I don't know, some data we're trying to load. Well, of course, if we want, yeah, okay, if we want to actually access that data, well, going back to primary storage, we can actually only access it, sort of from the CPU, if it's currently stored in RAM. Right, we can't access directly if it's on secondary storage or if it's in virtual memory. So what we can do is, let's say for example, I don't know, yeah, these pages here we don't need because maybe we've like minimized that program. Yeah, that program we're not actually doing any tasks in it currently. So what we can actually do is, yeah, okay, right, let's just sort of draw that here. Okay, so we can temporarily take these pages, we can then put them on secondary storage again, just temporarily. Let's just sort of draw this here as representing secondary storage, where we're putting that. And then the processes, right, the programs that we want to load, or the data we want to load, well, that can then be loaded into these pages that we made available, or yeah, into this sort of memory locations we made available in RAM. And then okay, yeah, and okay, we say this is like an ongoing process because maybe now we actually need this data, from sort of virtual memory back. So what we then do is then we find other pages we don't need. So let's say maybe this page here we don't need. Right, maybe, I don't know, let's say this page here we also don't need. And notice that pages don't have to be stored contiguously. So what contiguously means, basically just adjacent, right, neighbors. So we don't have to think, okay, we can only take, I don't know, pages like 2, 3, 4, 5, because they're next to each other. We could actually page out, I don't know, page, 100, obviously send it here to virtual memory. Right, we could also, of course, obviously have, I don't know, like page, yeah, like 1 million, right? And also, of course, we'll page it into virtual memory. All right, and likewise, when we page it back in, even though this here might actually be one program, right, one process, again, this doesn't have to be stored contiguously. So we can take the first page here, and we can, let's say, load it back into this location, or page it into this location. Right, we can then take the next page here, and let's say page it back into this location. Okay, so this is why paging is quite flexible, where if we break memory down into these fixed size, 4 kibibyte basically pages, right, then we can yeah, kind of like move things around, right, they don't have to be stored contiguously. Yeah, it's quite flexible like that. Okay, right, so I guess, yeah, now we just want to really explain this. So I guess they've already said that RAM becomes full. Right, so let's say virtual memory, let's say secondary storage. Right, secondary storage, yeah, I guess, well, space. Right, space can be allocated. Right, to temporarily. Right, and I guess really when we say allocated, that's basically just virtual memory. Yeah, that's really the definition of virtual memory. When we're kind of allocating secondary storage to temporarily hold data, well, yeah, I guess instructions data that was previously stored in RAM. Where it can be allocated to temporarily, right, store, I guess unused, I guess, yeah, idle, or yeah, I know, idle / unused. Yeah, well, let's say data, right, / instructions. Yeah, or I guess we could say pages, because again it's going to be stored in a page. Right, pages, yeah, from RAM. Yeah, okay, right, let's say, I know, yeah, this is called paging out. Yeah, okay, I think we probably don't really need to say, paging out. However, just to signify to the examiner that, this is actually what's happening, where we're taking pages from RAM, and of course we're temporarily putting them, yeah, on, well, yeah, the sort of virtual memory, or on kind of in secondary storage. Yeah, let's say to make room. Yeah, I guess to make room for the kind of video data that we're currently processing. Yeah, make room for the video data. Right, video data we are currently processing. Okay, right, and then yeah, let's talk about sort of paging back in. So let's say I don't know, yeah, when yeah, I guess when finished, and yeah, let's say right, when finished or not needed, right, when finished slash not used. Let's say the pages, yeah, the pages, well, I guess temporarily stored in virtual memory, or the pages in virtual memory. Right, the pages in virtual memory, right, can be, I guess, paged in, or yeah, loaded back. Right, paged in to RAM. I guess, yeah, where they can be accessed again by the CPU. Yeah, okay, where they can, yeah, I think access is fine. Right, yeah, where they can be accessed again, right, by the CPU. Yeah, and hopefully that should be enough for 3 marks. Right, so the computer uses solid state or flash memory storage. Give 2 features of solid state flash memory. Okay, so let's try then just to explain how these solid state or flash memory works, or yeah, for what flash memory devices work. So what we're going to have down here, I mean, honestly, it doesn't really matter what this is. I mean, here they call it substrate. Basically, it's just like metal. Now, of course, this is going to have electrons. So I'm just going to get E minus, right, for these electrons. Now what you're going to have the control gate. Now the control gate can have a charge, and this can either be a positive charge or it can be a negative charge. And basically this can be controlled, right? So either we can make this positive, right, or we can make it negative. Now this here, the floating gate, this basically corresponds to a bit. Now which way it is doesn't really matter. Let's say for our example, we can say that if there's electrons inside the floating gate, right, then let's say for example that means a 1, right, so if there are electrons that means a 1, right, if there's no electrons, right, that can be a 0, obviously, yeah, just a bit. So currently, yeah, okay, currently here then we see, well, there are electrons in the floating gate. Now what you want to think is, well, yeah, okay, right, so what kind of polarity, or yeah, what charge do we want to apply to this control gate in order to get the electrons out of the floating gate? And yeah, okay, the thing is, right, so we think basically the electrons only go kind of back and forward from here, right, so yeah, from the substrate to the floating gate. They actually can't pass through this insulator here, right? So how can we go from the control gate and get these electrons, obviously from the floating gate, you know, to go down back into the substrate here? And hopefully you realize that actually if we apply a negative charge, so let's go here, right, okay, if we apply a negative charge to the control gate, well, of course, right, this negative is then going to repel these electrons down, right? So that's kind of how we can go, let's say, from a 1 to a 0. Now, what we then have here, of course, okay, yeah, so all of these electrons are going to be empty, right? They're not going to be in the floating gate. They're going to be back down here in the substrate. Now, of course, if we then want to do the opposite, so if we want to go, where is it? Okay, yeah, if we want to go from no electrons in the floating gate, right, obviously to some electrons in the floating gate, well, then we can apply a positive charge to the control gate, because if we apply a positive charge, well, that's then going to attract these electrons back up, right? And of course, yeah, now the electrons are going to be back here in the floating gate. Right, so hopefully that makes sense. And I think a lot of people, they struggle with this because honestly, you know, when they hear the words like, yeah, transistors, capacitors, right, it's quite complex. Like, okay, yeah, if you just want a simple definition, again, just think, right, so the control gate, well, this is basically going to control whether it's a 1 or 0, right? That's why it's called control. And if we think, well, if we apply a negative charge, the electrons are going to be basically repelled out of the floating gate. Obviously, again, apply a positive charge, they're going to be attracted into the floating gate. Yeah, obviously just going, you know, between the floating gate and the substrate back and forward. All right, so yeah, hopefully that makes sense, kind of how that's working. So yeah, let's try and write an answer for that. So we can say what uses, I know, yeah, just uses what control, yeah, uses control gates to change, or yeah, I don't know, to sort of what, change the bit, yeah, change bit values. Or let's say, I know, yeah, by applying electrical charge. Yeah, I think that should be okay. Right, I think I'm probably gonna write, yeah, and and a floating gate to store the electrical charge. And floating gate or floating gate transistor. Transistor. To store electrical charge. And then I think for number 2 I'm going to write something completely different. So you can probably say it's going to be non-volatile. You can probably say there's going to be no moving parts. I guess we've said it uses electricity. So I think let's go here. Let's just say non-volatile. Let's say non-volatile because, and the reason for that is if we sort of go back to the diagram, basically it's because we've got the 2 insulators here. So if we have electrons stored in the floating gate, then because we've got an insulator, obviously here on top, but also another insulator here on the bottom, then basically these electrons will be trapped inside the floating gate. Technically they do actually leak out slowly, and this is why they say if you have an SSD, then they say actually you should turn it on, let's say at minimum once every 2 years. So if you've got some old laptop which you've not opened for like 5 years, then potentially some of the data on the SSD might have actually been lost or corrupted, because I guess over those 5 years, like some of these electrons will naturally leak out. Although generally that's a slow process. Alright, so that's why generally you say they're going to be trapped sort of inside the insulators, kind of in the short term. Alright, that's why it's going to be considered as non-volatile. So let's say that non-volatile because let's say charge is trapped, between insulators, inside the floating gate. I think that should be okay for 2 marks. Then we want to give 2 examples of solid state flash memory storage. So I guess we can just say SSD. And I think let's just write that. So solid state, solid state drive. And I guess the next one, let's just say USB. Of course, let's say like USB stick, because I guess technically USB is the protocol, right? Universal serial bus. So like USB stick, or I know USB like memory card or something. I guess USB flash drive. Then number 8, a robot is used to move car parts in a factory. One characteristic of the robot is that it has a mechanical structure. And we want to give 1 other characteristics of a robot. So I think there's about 3 things they usually say for a robot. 1, it has to be mechanical. 2, it has to be electrical. Let's say that. Let's say contains electrical components. And 3, I guess, usually they say it's going to have some degree of kind of autonomy, basically like autonomous nature. So it can operate kind of partly independently. Now, of course, a human will have to pre-program it in most cases. However, I guess once it's pre-programmed, then it can just operate by itself. It doesn't need a human to operate after that. So the robot has firmware. State what is meant by firmware. So I think we can say it's going to be low-level software. So low-level meaning it's kind of like close to machine code. So probably it's going to be C, C++, maybe Rust. It's not. So it's not going to be something high-level like Python. Now it could also be assembly. It could also be, I guess, something called microcode. So let's say low-level software. Let's say what that is directly kind of included on the hardware, or that's kind of pre-programmed onto the hardware. Let's say that low-level software, I guess pre-programmed or printed onto the hardware. Pre-programmed onto onto hardware. Or let's say to control. I guess control or manage communication with said hardware. To control and manage communication Okay, manage communication right between this hardware and the operating system. Right between yeah, this hardware right, and operating system. Let's go, yeah, OS. Okay, so to give an example, I think quite an easy example is if we think about a router. Now, a router is going to have firmware, and some of the things that that firmware is going to do on the router, if we think about the sort of what packet, yeah, I guess, okay, right, so not really packet switching, or sort of packet reordering, because I guess, well, packet reordering is really going to be done by the end device. Alright, but things like storing the routing tables, so it's going to basically take in an IP address, it's then going to look in its routing table for where to send this, yeah, sort of based on that kind of destination IP address. I guess other things that might be stored in the firmware, let's say if there's a DHCP server, so that's used to dynamically allocate IP addresses to devices on the network that request, and yeah, that's going to be what a private IP address. Well, okay, yeah, alright, so hang on, it's going to be a private IP address if it's a router, sort of like a home router. I mean, if it's your router, I mean, your router is actually going to request a public IP address, right, from your ISP. Also things like DNS, right, so DNS, that can be included on the firmware. Yeah, the actual kind of code used to implement the sort of DNS checks, right, the, yeah, you know, DNS protocol. Right then, C, so interrupts are generated when the robot's operating in the factory. Give two examples of interrupts that may be generated when the robot is in operation. Okay, we could say what, I know, yeah, hardware damage. Yeah, hardware damage, I don't know, let's say e.g. I don't know, yeah, some sensor is broken. Yeah, okay, and alright, I guess you can also just say like sensor values. I mean, that's also going to be interrupts. Yeah, because maybe the sensor has, I don't know, you know, detected something. Alright, so yeah, the sensor is going to send something, and I guess what the microprocessor is obviously going to process that. And if, for example, it detects that the sort of conditions outside the normal range, then it can generate an interrupt in order to affect the behavior of the robot. Yeah, e.g., I don't know, by, you know, turning down the speed or something. Yeah, just to make it safer. Alright, but I guess another one, like, yeah, less, okay, right, and obviously good tips for these questions. You know, don't write two things that are similar, because if you write, say, one, you know, hardware error, and then write another example of a hardware error, I mean, maybe they only give you 1 mark. So let's say software error, just go completely opposite. Alright, and I don't know, yeah, we can just say e.g. like divide by 0, or like wrong data type. Yeah, let's say like wrong data type. Yeah, let's say wrong data type assigned to variable. Alright, and I guess, yeah, software errors, I mean, you can think of many, right? You can say, let's say like array out of bounds, right? If an array has 5 elements, but you try to access element 6. Yeah, string out of bounds, right? If you try to access character 10 in a string of only 9 characters. Yeah, I guess like wrong number of parameters, you know, sort of various things. Right then, D, so give 2 advantages to the workers in the factory of using robots to move the car parts. So I guess what is like less physical strain. So yeah, the workers will be less tired, I guess. Let's say that, right, workers yeah, will be less tired. Yeah, okay, I don't know what, due to, I don't know what, you know, obviously, well, less physical, yeah, let's say what, less physical movement, I guess. Yeah, okay, so, and I guess obviously, like, in the exam, you probably want to be more specific. You'd want to say, what, due to less physical movement, you know, like by the workers, right, since the robot is doing it instead. Right, let's go safer. Right, workers, yeah, don't have to move, I guess, what, sharp or heavy, yeah, heavy car parts around. Right, don't have to move, I don't know, let's say sharp, right, sharp, heavy, maybe toxic, because, I don't know, maybe it's like covered in paint or something, right, toxic parts around the factory. Right, and then I think some other ones they often say for this, right, okay, yeah, of course, if they're talking about the factory, the advantage is where you say, well, it's cheaper in the long term because, you know, you don't have to pay the workers. because, well, of course, you sort of buy the robot once, then it just, you know, operates like 24/7 independently. Alright, so that's probably another one you could say. Yes, you say, well, the robots can operate 24/7, right, even if there's no workers there. You can probably also say, I guess, what the robots can probably be faster. I mean, yeah, the robots can probably move a lot faster than humans can, especially, you know, obviously over long distances. You could maybe mention like more precision, so the robot's going to be more precise. Yeah, although this is maybe not kind of like relevant if you're just talking about moving something from A to B. Yeah, because I guess generally that probably doesn't require that much precision. Right, anyway, the next one, so the robots have the ability to automatically adapt their own processes. I state the name of this ability, right, that's going to be machine learning. Of course, what they're taking the inputs, they're then obviously sort of processing that, right, learning from it. Yeah, seeing, well, was this successful, was it not successful? Of course, if it is successful, well, then it will try to basically sort of copy that behavior, right? If it was unsuccessful, well, then it will try different behavior, yeah, in the hope that this different behavior is more successful. And I guess it's kind of like an evolutionary thing, where basically like each iteration is hopefully going to get more and more successful. Yeah, although to be honest, of course, there are, you know, many different types of machine learning. Right, and I think this is going to be the last one. Right, so each employee in a finance company has a computer and an electronic account. Each computer has an operating system. One function of the operating system is to manage memory. Describe the role of the operating system in managing memory. Okay, so this is kind of quite similar to the one we mentioned, right? You can talk about paging, you can probably talk about virtual memory. I think something you'd probably want to mention more would be about allocating memory. So it's going to be responsible for allocating memory to process that request it. It's also going to ensure that two processes don't have access to the same memory. So I guess you can say what preventing memory corruption, yeah, preventing illegal access to memory. All right, so let's try and say some of that. Right, so yeah, the operating system. So it will allocate, or yeah, you could say like responsible for. So responsible for, let's say allocates memory. I guess we can say pages. Right, pages to processes that request them. Yeah, let's say what and ensures. Right, ensures two processes. Right, two processes never have access to the same memory. Yeah, well, let's say, I don't know, for security. Right, security. I guess you say what, privacy. Right, yeah, / integrity reasons. Right, okay, yeah, we can also say what also deallocates. So yeah, deallocates memory. Right, deallocates memory from processes. Right, processes when no longer needed. Okay, and I guess if we're talking about paging, we could say, well, it's responsible for managing the page table. Basically kind of keeping track of which process is stored in which particular page, or yeah, which particular, you know, combination of pages. Because as you remember, now in paging, the pages for a particular process don't have to be stored contiguously. So let's say you have, I don't know, some game. Well, maybe one page of that game is, you know, in sort of like memory address 0, but then another page is in memory address like 1 million. It doesn't have to be stored in, you know, memory address 1, right, then 2, then 3, then 4. Right, so let's sort of say that. Let's say maybe manages. Right, manages the page table. Yeah, to right, let's say and virtual memory. Page table and virtual memory to ensure, I guess, what, efficient. Yeah, I mean, is there another word? Maybe efficient. I guess maybe organised. Yeah, I think organised is maybe not the best word, but let's just write that anyway. Right, efficient and organised access. Right, of, yeah, I guess what, of memory. Or let's say even if RAM is full. Yeah, I think that should be fine. Right then, B, the finance company is concerned that hacker may perform a brute force attack to gain access to an employee's account. Describe how the hacker will perform the brute force attack. Right, so this basically means, okay, yeah, right, so they may have access to the username. Right, if they have access to the username, then it's going to be easier because, well, then they only have to iterate through different password combinations. If they don't know the username, well, then that's going to be much more difficult because then they have to try basically every combination of username and obviously all the combination of passwords too. Alright, but basically we can say, well, I guess, yeah, iterating or looping. Right, iterating right through, let's say huge numbers, like, yeah, I don't know, huge numbers of combinations. Huge numbers of combinations. Right, of login credentials. Right, login credentials. So I guess, well, obviously, yeah, you could say what username. Right, usernames, right, passwords. Right, in the hope. Right, in the hope that one is successful. Right, okay, and I guess we can say what usually is automated, with some kind of brute force software. I think one popular one, right, is called John the Ripper. Yeah, people can search that if they want to have a look at that. Right, and often these are going to use a word list. So yeah, I guess what a word list or a password list. Now, if you have a word list, I mean that's kind of what it says, right? Basically, it's just going to be a dictionary of thousands of different words. Because if we think like most people don't have completely random passwords. I mean, most people don't have a password like hash, right? For let's say 8, right? That say at. Yeah, okay, right. So most people don't have passwords like this because just because it's too difficult to remember. In reality, I don't know, like yeah, all right. So let's say someone might have a password like, I don't know, say football. Let's say football 1 2 3. All right. So if you had a word list, of course, well that's going to contain words like football. And then you just try different combinations. So you try football, but then of course you try football 1, football 2, football 3, obviously, etc. All right, so let's say, yeah, usually automated, right, and can use word lists. Right, can use word lists to, let's say, increase. Slash speed up, right, the chance, the chance of finding, finding successful combinations, or successful passwords, basically. Let's say you're login credentials. Yeah, okay, alright, and some people might think, well, if you use a word list, of course, you're not trying every single combination, therefore, you might potentially miss it. Let's say, what if their password was, I don't know, sort of out of football, then hash, for example, and let's say if you didn't try this exact combination, right? However, let's say if it's an actual hacker, now maybe they have like 100 people's, sort of different usernames which they've got access to. Now, even if 99% of them, the word list doesn't work, right? Potentially you only need access to one of them. So that's why it's kind of better. Because like honestly, like if you have let's say a list of like the million most common passwords, I mean if you have 100 people, like it's almost certain that probably at least, I don't know, maybe, I don't know, like 20-30% are going to be using passwords that are on that 1 million most common password list. So yeah, that's why it's kind of better just to use these word lists, right, rather than trying every single combination, because yeah, there's just like a kind of huge number if you do that. Right, anyway, so the next one, give 3 cybersecurity solutions that could be used to help prevent brute force attack from being successful. Okay, so I guess we can say what, limit the login attempts. Limit login attempts. I don't know, yeah, e.g., let's say what, 5 attempts per minute. And then, for example, if you've had more than that, well, then you get, sort of temporary locked out. I guess if it's a website, I mean, you could say what, block based on IP. Let's say that, yeah, block IP addresses. Right, block IP addresses suspected, right, of brute forcing. Alright, and then I guess the third one, I mean, yeah, I guess this is kind of what we said, right? So you just say, well, use strong passwords. You can also say, well, biometric. You can say, what, two-factor authentication. Let's go, what, I know, yeah, use strong passwords. Alright, and again, like maybe here you want to give an example, right? Let's say e.g., I know, yeah, well, alright, let's say lower, upper, right, numbers, right, symbols. Yeah, I'm not going to write that, although in the exam you can probably write that if you want. Right, I think just two more. So the company uses a digital currency to purchase a new car. State what is meant by digital currency. Right, so I think this is just a definition you have to remember. Basically, it's a currency that only exists electronically. So, you know, you don't have like physical paper money, for example. So yeah, let's say that, right, a currency that only only exists, well, I guess, yeah, electronically, right, or digitally. Yeah, let's say right, electronically / digitally. Right, okay. Yeah, I think that should be enough. Right, then the digital currency uses a process that involves a digital ledger. The ledger has the ledger has timestamped transactions that cannot be altered, and give the name of the process. Okay, so right, that's basically the process of creating the blockchain. Yeah, alright, and I guess here you can kind of really say digital ledger or blockchain. You can use those kind of interchangeably. And actually, I did actually search, because for me, when people say blockchain, I mean, to me, I think of the actual ledger. Yeah, I think of the actual data of, you know, the sort of record of all the transactions, or yeah, all the senders, all the receivers, you know, how much is sent. Of course, like that's actually going to be that's going to vary. For example, something like Bitcoin, right? There's actually quite a lot of information that's stored on there. I guess, yes, some of the other, well, let's say cryptocurrencies, although of course, right, a digital currency doesn't have to be a cryptocurrency. But if you do talk about cryptocurrencies specifically, of course, well, some of them are, well, more anonymous than Bitcoin. Yeah, they actually don't include, for example, the sender. Alright, but anyway, yeah, so I think the blockchain, that's kind of two purposes for the name. Right, so yeah, one, you can say the blockchain is actually the physical ledger, or well, the digital ledger. Alright, however, yeah, I guess people also use blockchain to refer to the actual process of creating the blockchain. Well, yeah, the process of, well, of course, you know, storing all this data. Yeah, the transactions. Alright, and I think, yeah, that's all of the questions. Right now, guys, I mean, that's super long, maybe even close to 2 hours. Although, yeah, hopefully that video is useful. And as always, I mean, any questions, just ask in the comments. And I'll see you again in the next video.